This week or this lecture we will discuss how to find the properties across a moving shock. When a moving shock is something that what we are going to consider is a shock that is moving in a stagnant fluid. Okay. So, we will not consider a moving shock in a moving fluid. So, the example that we are going to consider for this course is just a shock that is moving in a stagnant fluid, like a shock that is moving when there is a bomb explosion. So, you have an explosion and there is a shock, and this shock moves across the space, and as it moves it changes the properties behind the shock. So, till then there is no change. As soon as the shock crosses a point, the properties behind the shock changes. Okay. So, that is what we will consider. And we will consider only a normal shock for the time being. So, I have a shock which is moving with some velocity. So, this is a stagnant fluid or gas, and as it moves it changes the properties here. Okay. So, here is my Py, My and Ty. So, before the shock is my Mx, Px, Tx. So, the fluid here has 0 velocity before. So, V equals 0 in this case, but as the shock comes and hits the point, the velocity changes. So, I have a Vy. Okay. Now, we will do the proper notations now. So, I have a shock and I am an observer standing outside this. So, there is a frame of reference associated with the observer, like what we had done when we evaluated the velocity of sound. So, I have a pressure wave that is moving. Now, here the pressure wave is not infinitesimally small, but a finite value of pressure wave that is moving, which is a shock, unlike the sound velocity, which is an infinitesimally small pressure wave. So, I call this as I will use the notations. So, this is a moving shock or stationary observer. Okay. So, the fluid, this is my direction of shock moving. So, any locations before the shock is 1, any location after the shock is 2. And as soon as the shock hits the point, the velocity here would change from 0 to some value. Okay. So, V1 is 0 here, V2 is V. So, this is an unsteady problem. So, I have a shock moving and a stationary observer. So, I see the shock that is moving across. Now, Vs is constant. Or I have a uniform velocity. Okay. In that case, like what we have done for our when we derived our velocity of sound, I can have an observer that moves along with the shock and try to evaluate, convert this unsteady problem to a steady problem. Okay. So, I would use a moving observer or a stationary shock. So, if I am moving along with the shock, I would feel the shock to be stationary. if the shock is stationary, I can use the relations that we have derived in the previous classes to evaluate the properties. Okay. So, let us see what are the properties that would change when we do this. So, here I would have x and y, x is before the shock, y is after the shock or front of the shock, behind the shock, as we called that in the stationary shock, stationary shock. So, the shock, if you are an observer standing in the shock, I would see the fluid that is approaching me with a velocity Vs, and I would see the fluid that behind me receding at V minus Vs or Vs minus V. So, I am moving along with the shock. So, for example, in this case I am standing here and watching the shock. So, that would have a velocity Vs which is moving past. So, if I am moving along with the shock, I would see the fluid that is approaching me with Vs and receding me with V minus Vs. Okay, that is what precisely what we have. So, my Vx is Vs, Vy as this. Previously we had V1 is 0 and V2 as V. Here my Vx is Vs and Vy is. In fact, that is the only notation that we will use. As long as we do not confuse these two notations, we are into the problem. Okay. So, we have assumed constant Vs. Now, what is a static quantity? How do we measure static quantity? For example, P1 or T, P or T. So, if we move along with the fluid and measure my pressure, then I am actually measuring what? My static pressure. If I bring that rest and measure my pressure, I get stagnation pressure. So, if I have a fluid, if I am moving along with the particle and measure my pressure or temperature, I would get my static pressure or static temperature. If I isentropically bring it down to 0 velocity and measure my temperature or pressure, it is called the quantity that we are measuring as the stagnation pressure and temperature. This is something which we had defined it during our definition of stagnation state. So, now we have a situation here where we are moving along with the shock. So, if I measure the pressure that moving, if I move along with the shock, I would be measuring my static pressure. Okay. If I measure the temperature and I move along with it, it will be static temperature. Okay. So, if I look at case 1 where I have a stationary observer and I have a shock that is moving. So, the pressure here before the shock approaches, it is a stagnant fluid. So, the pressure here is my stagnation pressure, so which is also my static pressure. So, my P1 is also equal to my P01, okay, and hence my T1 that is measured is also equal to my T01. Okay. So, that is the first information we have. Now we go to the other coordinate system, case 2, where there is a standing shock now, fluid approaching with Vs and fluid receding with Vs minus V. Since it is a standing shock, we know that the stagnation temperatures are the same. So, so I will write here as two cases. One is stationary observer, stationary observer and moving observer. Or you can write this as moving shock and stationary shock. So, in stationary observer, my P01 is same as my P1 and my T01 is same as my T1. In a moving observer, we have a standing shock, which means my T0x is same as my T0y. Okay. And now the static quantities which we had measured from the moving stationary coordinates is also same as my moving coordinates, because I am moving along with my fluid. So, the Px that is measured here is same as my P1. So, I would write this quantity. So, the Px is what? The static pressure which is measured when I move along with the fluid, that is same as my P1. Okay. Likewise, my Tx, which is the temperature that is measured when I move along with the shock, is the same as my T1. So, my T1 is same as my Tx. Now, I use continuity equations, momentum equation and other set of equation to derive the following relations. So, as I wrote here, I would complete this. Vx is my Vs in the moving coordinates, Vy is my Vs minus V, V1 is 0, V2 is V. As long as we are comfortable with this notation, we can proceed further. Okay. And the static quantities after the shock is also, so you can write P2 is my Py and Py is my P2. Likewise, T2 also, because that is a static quantity which is not changing because of the coordinates, whether it is moving or this thing. In any case, the static quantity is measured when you move along with the fluid. So, whether the observer changes its position or not, it is not going to change your definition of your static quantity. So, the static quantities are going to be the same. Okay. So, now we apply the momentum equations and other things. So, the notation I would again rephrase it here. So, stationary coordinates or observer, I have used x and y, and moving coordinates I have used 1 and 2. This notation we would keep it. This notation is very important, unlike in other classes where we could mess up with our notation and still get a convincing argument. Here, if we mess up with the notation, we are going to mess up with the arguments. Okay. So, now I have mx, mx is Vx by Vs by Ax. mx is Vs by Ax. Yeah, sorry. Stationary coordinates is 1 and 2. Moving coordinates is x and y. So, we keep this notation which defines new quantities. Mach number xy before and Mach number across the shock in a moving coordinate system, and Mach number across the shock in a stationary coordinate system. So, we define Vx by Ax, Vx is Vs. So, I would write Vs by Ax, and My is Vy by Ay, which is Vs minus V by Ay. M1 is V1 by A1, which is 0. M2 is V by A2, which is V by V2 by A2, which is V by A2. Okay. So, my Ax is root gamma r Tx, which is same as root gamma T1, which is same as my A1. Ay is root gamma Ty, which is same as root gamma T2, which is my A2. Okay, so my Ax is same as my A2, Ay is same as my A2 because of this quantity. So, Ay is same as A2, A2 is same as my Ay, and A1 is same as my Ax. So, I can write my My in terms of M1. So, I will assuming keeping this notation intact, I am going to rub this particular portion. So, my My is Vs minus V by Ay, which is Vs minus Ay minus V by Ay, which I multiply by Ax minus V by Ay is V by A2. V by A2 is my M2. So, I can write this as Ax by Ay into Vs by Ax is Mx minus M2. Okay. So, if I replace this with gamma RT, I can write it in terms of T. Now, we know T1 equals Tx, which is also T01. So, T0 x by Tx is 1 plus gamma minus 1 by 2 into mx square. T0y by Ty is 1 plus gamma minus 1 by 2 my square. But Ty is also T2. So, I can replace this with 2. So, I can write okay. Likewise, I can write for P also. P0 x by Px is 1 plus gamma minus 1 by 2 mx square into to the power gamma by gamma minus 1. Now, we also know Px equals P1 equals P01. So, I can replace this with these quantities, any one of these quantities, which is equal to P0 x by P1, which is equal to P0 x by P01. Likewise, P0 y by Py is 1 plus gamma minus 1 by 2 my square to the power gamma by gamma minus 1, which is equal to P0 y by P2, because the static quantities are same. Okay. Now, I am not going to rub this, but I will rub this portion and write this equation. Maybe I will rewrite that equation here. My equals Ax plus Ay into Mx minus M2. Okay. So, we know across the standing shock, which is my moving coordinate system, my T0 x equals T0 y. So, you can eventually try to find what is T01 minus T0, T02 minus T01 not equal to T0y minus T0x, whereas my T2 minus T1 is same as my Tx, Ty minus Tx. So, you can show this. So, my T02 minus T01 is T1 T2 into 1 plus gamma minus 1 by 2 M2 square minus T1 into 1 plus gamma minus 1 by 2 into M1 square. M1 is 0. So, this term is 0. So, I have T2 minus T1. I will write the whole thing, 1 plus gamma minus 1 by 2 M2 square minus T1. I take T2 minus T1 plus T2 into gamma minus 1 by 2 into M2 square, which I replace m2 in terms of Mach number and m2 in terms of velocity, v2 which is v by a2 which is ay or a2, and replace a2 as gamma r t2. So, I strike t2 minus t2. So, this would be t2 minus t1 plus gamma minus 1 by 2 into r gamma into v2 square. Now, if I substitute t2 minus t1 in terms of velocity, then I can get this whole equation in terms of velocity, which is not equal to this quantity, which I will do that here. So, this is my equation equation 1. Now, I would try to find T2 minus T1. So, my Ty minus Tx is my T2 minus T1. So, I would find this is again T y by Ty is 1 plus gamma plus 1 minus 1 by 2 into my square, and T0x by T0 Tx equals 1 plus gamma minus 1 by 2 mx square. Since T0y equals T0x, I can write this as Ty 1 plus gamma minus 1 by 2 my square equals Tx into 1 plus gamma minus 1 by 2 mx square. So, Ty minus Tx equals Tx into gamma minus 1 by 2 mx square minus Ty into gamma minus 1 by 2 my square. Okay. Which again I replace this in terms of velocity of sound and velocity of the fluid. So, Tx into gamma minus 1 by 2 into Vx, Vx is Vs square divided by gamma r Tx minus Ty into gamma minus 1 by 2 my. My is Vy by A, Vy by Ay, Vy is Vs minus V the whole square divided by gamma r Ty. So, Tx cancels, Ty cancels, I end up with gamma minus 1 by 2 r gamma into Vs square minus Vs the whole square. So, this is nothing but gamma minus 1 by 2 gamma r, Vs and Vs cancels out. So, you end up with 2 Vs V minus V square. Okay, which is also equal to my T2 minus T1 because the static quantities are same. So, if I substitute this equation, equation 2 in 1, substituting equation 2 in 1, I would get T02 minus T01 as gamma minus 1 by 2 gamma r within brackets 2 Vs V minus V square, then this plus V square, which is nothing but this quantity 2 minus T01 is gamma minus 1 by 2 gamma r, 2 and cancel, so Vs V. So T02 minus T01, I will write that here, T02 minus T01 is gamma minus 1 divided by R gamma Vs V, whereas T0x equals T0y. So, that is, this difference is different from T0y minus T0x. So, your Tx is also in terms of Ty minus Tx is gamma minus 1 by gamma r to 2 Vs V minus V square, which is also equal to T0 T2 minus T1. Okay. Which again is not equal to T0y minus T0x. So, this is equal to T2 minus T1. Okay, so, this difference in stagnation temperature is not the same, but difference in static temperature is the same. Okay. So, if you know these properties, you can find the other properties that is happening in a shock that is moving. So, in the next class we will do a numerical problem and try to understand these two coordinate system and evaluate all the properties in the moving coordinates and in the stationary coordinates. This notation we would keep the same. This is very important because that is what it deals all with this. So, stationary coordinates 1 and 2, moving coordinates x and y for this particular course. Okay. Thank you.